Let's talk about solving a family of differential equations called first-order linear differential equations. They have this standard form. Equations which can be placed into this form, dy dx plus p of x times y equals q of x, are first-order linear differential equations. Another notation is to take the dy dx and express this as y prime, and it's a little easier to manipulate, I think, like this. Notice that the p of x is just a coefficient of y, and p of x and q of x, by the way, are continuous functions. They're just expressions in terms of x, and we can think about them like that. Now, part of the process of solving this kind of differential equation is to identify what's called an integrating factor. And the integrating factor is calculated as e to the integral of p of x dx. And the p of x just comes from right up here. Now, it turns out that if you take the integrating factor and multiply it through the equation and then solve the equation, you find that y is equal to this expression. Now, the expression looks pretty complicated as we see it right here, and we could take a path to solution here of just memorizing this expression and then plugging in the information from our particular differential equation into this form and then grinding out an answer, kind of like we do with the quadratic formula. But I suggest a different tactic. I suggest that we identify the integrating factor and actually multiply it out and then solve in order to arrive at this. But I want to show you why this works. I want to show you why multiplying through by the integrating factor turns out to give us a solution here. It involves a really intriguing situation, but it starts out like this. We take our standard form, we multiply through by the integrating factor, and here I'm just showing y prime times integrating factor, p of x times y times integrating factor, right side times integrating factor. Okay, now here's the intriguing part. This sum turns out to be y times the integrating factor all prime, that is the derivative of this product. Now, this is intriguing because we haven't talked about or even thought about using the notion of the product rule involved in derivative in order to factor. You see, we're kind of using it in reverse as a factoring mechanism. Kind of like that's what's going on here. We can kind of verify that it works, though, by going back in the other direction. You see, this product, the derivative of the product would be, well, let's see, it would be the derivative of this factor times that factor, that's what we have here, then plus this factor times the derivative of that. So it's y times the derivative of this. Well, the derivative of this, you see, it's the e to the u du business. You see, and the derivative of this is p of x. So it's p of x times integrating factor, you see. And that's how we get this. But it's the notion that when we go through this process and identify integrating factor, multiply through by it, we can go through this sort of factoring process very, very quickly. It's just y times the integrating factor. That's all there is to it. Now, once we get to this point, we can integrate on both sides. When we integrate here, we get this. Integrate here, we get this. And now, dividing on both sides by the integrating factor or multiplying by 1 over the integrating factor, we get the expression that's expected, the one that we had written over here earlier. Now, let's take a couple of examples. Suppose we want to find the general solution of this, and we identify it as our first-order linear differential equation because we have a y prime here, we have a y here, we have an expression on the right side. And we can identify, now notice an important aspect of this is that our coefficient here is 1. If it's not 1, we have to make it 1 in order to put this into standard form. But it is 1, it is in standard form, and now we identify the p of x, q of x, and the integrating factor. Now the p of x is very, very important. The p of x is the coefficient of the y, and it's just 1 in this case. The q of x is the e to the x power. All right, integrating factor is e to the integral of p of x dx. But the p of x is just 1, so it's the integral of 1 dx, you see, or it is e to the x power. So now we take this integrating factor and multiply it through our equation in standard form. Here's our equation in standard form. Multiply through by e to the x, so y prime times e to the x plus y times e to the x equals e to the x times e to the x. You see, and now we simplify on the right side. And the intriguing part here is that this turns out to be y times the integrating factor, the derivative of that product, you see. All right, now we integrate on both sides and we get the y times e to the x. And on the right we want the integral of e to the 2x dx. Now here we have a little manipulation to perform. You know, it's the e to the u du idea that we're trying to establish right here. And we can do that rather easily. Let's come up top. We have the left side as it was before. We introduce a 1/2 here and a 2 inside to get this e to the u du business in here. And now the integral turns out to be e to the 2x power. And so we have 1/2 e to the 2x plus c, and now to clear this e to the x, we can divide on both sides by e to the x or multiply by e to the negative x if we want to, and that's what I've elected to do. So e to the negative x multiplying on both sides, we have e to the negative x times all of this, and so we get this as the result. Here's another one. Now in this one, we're not in standard form just yet. We don't have a coefficient of y prime as 1. We have to cause that to occur, and we do it by dividing through by x. I divide here by x and I get the y prime as expected. When I divide here by x, this becomes negative 2y over x. But I'd like to show a distinct coefficient of the y, so I want to write it like this. It makes it a little easier to identify p of x in the next step. And over here, when I divide by x, I get x. So p of x is negative 2 over x. The q of x is x, the right side. The integrating factor is e to the integral of p of x dx, but p of x is the negative 2 over x. You see, negative 2 over x. Now, e to this integral turns out to be 1 over x squared. There's a little manipulation that's necessary right here, but I'm confident that we've done this enough times before to where we can get to this business. So our integrating factor is 1 over x squared. The important point here is to take our equation in standard form and multiply through by the integrating factor. So it's y prime times integrating factor minus the next term you see times integrating factor, right side times integrating factor. And now on the left side, the situation is predictable. We have the derivative of the product of y times the integrating factor. And that's all there is to it. And now we're pretty much home free with just a little manipulation. We integrate on both sides, giving us this. And on the right side, we have the integral of the 1 over x dx. And from here, I did two things in one step. The integral here is the natural log of the absolute value of x plus a constant. So we have actually two terms over here. And I'm clearing this at the same time. I'm multiplying on both sides by x squared. So when I multiply over here by x squared, I'm left with y. On the right side, I have to multiply those two terms by x squared. So it's x squared times ln absolute x, and then that constant times the x squared as well. Another family of differential equations that can be solved using a little substitution and the method that we talked about earlier is called Bernoulli equations. Now, Bernoulli equations take on this form. Notice the left side looks very much like the first order linear differential equations we looked at before. But over here, we have kind of an extra factor. We have this y to the n power. Now, when that factor is introduced, we have to make a substitution here. And this is how the situation flows. We define some letter like z, could be v, could be another letter, but I'm calling it z here. Define z as y to the 1 minus n. Whatever that n is, then z is y to the 1 minus n. Z prime then is, well, let's see, it's 1 minus n times y to the 1 minus n minus 1, which is minus n, you see, for this exponent. And then since this is the derivative of z with respect to x, and therefore this is a y prime factor that has to be introduced here. All right, now with all of this, we go through and we multiply throughout the original equation by these two factors. You see, just those two factors. Multiply by those two factors times the y prime and we get this. These two factors times this rascal, we get this. These two factors times the right side and we get all of this business. Why is this important? Well, because this is nothing more than z prime. Now, z prime is the derivative of z with respect to x. So the z prime is here, and then we kind of clean up the rest of it. This y to the negative n times y is y to the 1 minus n. But oh, happy day, we have a nice substitution here as well, because after all, notice that z is y to the 1 minus n. So this y to the 1 minus n in the next step becomes z, or we can substitute z for it. And then over on the right side, that kind of takes care of itself. Notice the y to the negative n, y to the n kind of go out. Now, from here, we solve this using the methods that we talked about before. So we solve for z, and then we just substitute back what we found for z up here. Here's how it all works with a problem. We have, this is our equation we want to solve. And notice that on the right side, we have y to the negative 3 power. And this factor is what causes this equation to become Bernoulli. All right, now we want to identify the z idea. Now z is y to the 1 minus n, but the n is negative 3. So 1 minus negative 3, that's 1 plus 3 or 4. So y to the 4th is our z value here. Now z prime would be, let's see, it would be 4y cubed times y prime. Now we identify this part of that z prime. You see, these two factors we're going to multiply times every one of these guys upstairs. So it's 4y cubed times y prime, 4y cubed times xy. You see, and I'm simplifying a little, I'm getting a little ahead of myself, but it's 4y cubed times the xy, then it's 4y cubed times the right side. So we have all of this. Now let's clean up a little bit. This part of it becomes, this is just this. You see, that's the z prime. You see, we're putting this into a form where it is a first order linear differential equation so that we can deal with it using the techniques that we had before. And now some of these factors will give us the z. Well, we might look back up here. Z is y to the 4th. Well, y cubed times y is y to the 4th. So these two factors together give us the z, so it's 4x times z. And on the right side, we clean up the mess a little bit and we get this. Now we go forward with the idea of solving this for z. And the p of x is 4x. You see, it's the coefficient of the z here. The integrating factor is the e to the integral of px dx. Px is 4x, so it's the integral of 4x dx. That turns out to be e to the 2x squared. All right, so now that we have that integrating factor, we're going to take that integrating factor and multiply times all of these terms. Now I've done that up here. It's the z prime times integrating factor. Next term times integrating factor. Right side times integrating factor. And then we go through that little interesting step where we go through kind of a factorization process here. So we have the derivative of the product of z times the integrating factor. And on the right side, we just clean it up as we normally would. We have e to these exponents, and collecting the exponents, we get x squared for the new exponent on e. Now we integrate on both sides. Integrating over here, we get the two factors involved. Integrating on the right side, well, let's see. We have the integral of the 4x e to the x squared. Now remember, we're putting this into the e to the u du, but the du here, the du for the x squared is 2x. We need a 2x right here, so I'm separating the 4 as the 2 times 2 inside. And now the integral becomes the e to the x squared, you see, and then plus the c. So 2e to the x squared plus c on the right side. Now we isolate the z by multiplying through by e to the negative 2x squared. So we multiply over here by e to the negative 2x squared and they go out. Multiply here by e to the negative 2x squared. Multiply here by e to the negative 2x squared, and we get all of this business. And then once again we're cleaning up. We have e to the x squared times e to the negative 2x squared. Adding those exponents, we get minus x squared for the new exponent. And over here we simply bring down. Now at this point, you see, we have our equation. We've solved this for z, and all we have to do is back substitute. We just kind of look up above over here. We found z to be y to the fourth. So we just make that substitution and boom, we're finished.